And you're up, Laura.
All right, thank you so much, Gary. It's such a pleasure to be here. Thank you for inviting me to give this presentation. As I was telling Gary earlier, it's been a little while since I've looked. I know it's been only a year, but when we switch off to another species, your previous species just gets buried deep in your memories. So as Gary said, I'm going to be talking about the stock assessment we did for the Albemarle Sound Roanoke River stock here in North Carolina. And I'm just going to jump right into it. Okay, so here's a map of coastal North Carolina, and our unit stock for the stock assessment included all striped bass within the Albemarle Sound and Roanoke River management area. So those labeled the ASMA and the RRMA. So the ASMA, Albemarle Sound management area, and RRMA is the Roanoke River management area. The CSMA is our central southern management area. That's a separate stock that was not included in this stock assessment. So the division of marine fisheries manages commercial and recreational harvest in the ASMA, and our counterparts at the Wildlife Resources Commission manages recreational harvest in the RRMA. And just want to note that the spawning grounds for the AR stock are located in the Roanoke River near Weldon, and that's, I thought we had it starred, but we don't. Sorry about that. My geography is terrible. Okay, so on this graph, we're showing landings for the ASMA commercial sector and recreational landings for both the ASMA and the RRMA. Here on the y-axis, we have pounds, and the two solid lines, the blue and green lines, show our total allowable landings, or TAL, that have been in place since 1991. And one thing you can notice is that since about the mid-2000s, neither sector, that's neither the commercial or recreational sector, reached their TAL in most of the years in the rest of that time series. Even after the 2014 revision that reduced the TAL, starting in 2015 from 550,000 pounds to almost half of that to 275,000 pounds, harvested still did not reach the TAL. Okay, I'm going to jump right into the model setup. This is our stock assessment model. We use a software called Stock Synthesis. This is used worldwide. It is a forward projecting length-based age structure software program. The version we used was the version that was the most recent at the time, if you're interested, version 3.30.14. And we use this to estimate the population parameters and also our reference points. We modeled the AR Albemarle Roanoke stock as a single stock, a single season. So no seasons within the year, just one season. We modeled two sexes and based on a calendar year, 1991 through 2017. And the reason we chose 1991 as the start year is because that was the earliest year that we had landings for the Albemarle Sound recreational fleet. And 2017 was the terminal year because when we started the assessment process, obviously that was the most, the year where the most complete recent data were available. The maximum age observed at the time that started the assessment was 17. We've since seen an older age fish. I believe it was a 25-year-old. So next assessment, we'll have to revisit that maximum age. And based on a recommendation from the model developer, we used an age 15 plus group. Oops, wrong way. So we had 4 fleets to organize our removals. We had the ASMA commercial fishery, and then those abbreviations you'll see at the end on behind each fleet are the abbreviations you'll see on the figures and tables. The ASMA recreational fishery, and the RRMA recreational fleet was divided into both harvest and discards. And this was a recommendation from the peer review panel because we had some trouble in the early runs fitting the length frequency distributions when the harvest and discards were combined. Show you some of the data. These are the ASMA commercial landings that went into the model starting in 1991 through 2017. And you can see that they're variable and highest in the mid 2000s, and then they decline. Recreational harvest for the Albemarle Sound and the Roanoke River are shown here. The units, I forgot to mention, the units for the commercial landings were metric tons. The units here are thousands of fish on the y-axis. And here landings peak a bit earlier than the commercial landings. Here they're peaking in the early 2000s. We also included commercial and recreational discards, and these are dead discards. And we have those for the Albemarle Sound commercial fleet, the Albemarle Sound recreational fleet, and the Roanoke River recreational fleet. Our fishery independence data comes from 4 surveys. We have a survey of juvenile abundance, that's also known as the Program 100 survey, and the abbreviations is given there that you'll see on the graphs. This is a measure of age 0 recruitment. The independent gillnet survey has 2 components, a fall-winter component, that's what the FW stands for, and a spring component, the SPR. And we also have a Roanoke River electrofishing survey that occurs on the spawning grounds. We assume that the surveys had a linear relation to stock size. So what that means is that when the survey index goes up, we're assuming that the population is also going up. And likewise, if the survey index goes down, the population is going down. We also assume that a constant catchability over time. Now I'm going to show you what the trends for the indices look like. Here, this is our the Program 100 Juvenile Survey Index, our index of age 0 recruitment. And it's variable, not much trend, except that I guess there's a general decline over the time series. And what's concerning is the very low values in the terminal year of the time series. Here we have the fall-winter component of the independent gillnet survey, or Program 135. And starting about 2007, there's a decline through the end of the time series. Again, in the spring component, you can see there's another decline at the end of the time series. It starts a little bit later, starting in 2013. And maybe at the very end, there could be a little bit of an increase, but that's just 1 year. It's hard to say. And finally, our electrofishing index also shows sort of a not as steep, but declining trend through the end of the time series, starting in about the mid-2000s. We had a lot of biological data that went into the model, and here it's summarized by source and type for the length and age data that were input into the model and the years for which those data were available. If the years are highlighted in bold, that means that those data were available by sex. So for the age data, because we didn't have any information to the contrary, we assumed that they were associated with small bias and negligible imprecision. But you can see that the biological data are coming from both fisheries dependent and independent sources. So we use parameters of the von Bert age-length relationship, and we estimated them outside of the model and fit it to fractional ages using a weighted approach. And the weighting is based on the number of the number of observations at each fractional age. And this shows, you can see the solid black line is the best fit for those parameters that are listed there for both the females and the males. As far as natural mortality, the peer review panel was very interested in basing natural mortality on values available from empirical studies. And there were some tagging studies in the literature that we presented at the peer review workshop. And so our working group explored a number of options and found that fixing natural mortality at an age constant value derived from those empirical studies was the best option. And so we assumed in our very final base run, we assumed a value of 0.4. We assumed that for both sexes, across ages, and constant over time. Because that really was, we had a lot of trouble with natural mortality in this model, and this seemed to be the only option that really worked and that also the peer reviewers were satisfied with. We used age-based maturity and assumed that the eggs were equivalent to spawning biomass. This figure shows that all the striped bass are 100% mature by age 5, nearly 100% at age 4, and about 30% mature at age 3. For the stock recruit relationship, we assumed a Beverton-Holt curve with log normal deviations. Steepness was fixed at 0.9 based on a recommendation from the model developer, as there was no evidence of a strong stock recruit relationship. The variance in recruitment was fixed at 0.6. That's just a typical value that this is fixed at. And we also assumed a non-equilibrium age structure at this time of the time series. There's a feature in stock synthesis, the equilibrium catch feature, and the model developer, and I've mentioned him several times, he was just invaluable in helping us develop this model, but he suggested implementing this feature. And so when you use this feature, there's usually 2 common assumptions. The first approach starts the model as far back in time as necessary to satisfy the notion that the period prior to the estimation of dynamics was in an unfished or nearly unfished state, so like a virgin state. But for striped bass, we don't have reliable catch records back to the start of the fishery. So the second approach was used, which is to estimate where we can the initial conditions, assuming equilibrium catch. And that equilibrium catch is the catch that's taken from a fish stock when it's in equilibrium with removals and natural mortality, balanced by stable recruitment and growth. Just to mention the different selectivity curves that we used for each of our fleets and our surveys. So you can see most of them are asymptotic. For the AR commercial fishery and the program 135, or the independent gill net survey fall winter survey, we use cubic splines just because we initially were using a double normal curve to produce a dome shape for these 2, but it just was not even though it's super flexible, it just wasn't flexible enough, and not as flexible as a cubic spline. So you can specify how many nodes, or basically twists and turns, there are in that curve to allow the fitting to the length frequency data. And then for the Roanoke River Recreational Harvest, we worked with the peer reviewers and decided that we would fix that selectivity to match the protective slot, and that's shown in the graph there on the right-hand side. So stock synthesis assumes an error distribution for each data component. For the individual observations, there's a variance assigned to each observation, typically a standard error, and that's empirically derived where it's possible. And if you're familiar with the Francis 2011 paper, these are known as stage 1 weights. For our error structure is listed here. Log normal for landings and harvest, as well as the survey indices. We assumed a normal distribution for the discards and a multinomial distribution for the length and age data. A little more about model weighting. So in addition to the stage 1 weights of Francis, we also applied the stage 2 weights. And so these stage 2 weights are emphasizing the survey index signals over the composition data, because these models tend to put, when there's no weighting, these models will tend to put a lot of emphasis on the age and length composition data. But the reviewers really wanted to see a better fit to the survey indices. And so applying these stage 2 weights was consistent with their interests. Now, lambda weights aren't applied to the individual observations. They're applied to data sources sort of as a whole. So you have, the survey age data, the fishery age data, each one has a lambda weight associated with it. And when you don't have other information, you usually just assign the lambda weight for each data component set equal to 1. So our age data are typically associated with low effective sample sizes, but they can still drive these estimates of population scale. So the model developer, he recommended reducing the lambda weights for our age data to 0.25. So we did that, and the peer reviewers agreed with that decision. For our diagnostic checks, we had a number of those. The inversion of the Hessian, which basically means you can calculate estimates of error around your population estimates. Your convergence criteria set just at a standard of 0.0001. We also did a jitter analysis, and that's where you take your initial starting guesses and you jitter them. I think we jittered ours by 10%. And so what you're doing is you're running the model maybe 50 to 100 different times at different starting values, but within the reasonable range, and seeing if you still land on the same results as your base run. And this gives you indication that you're at your global solution. Then we compared our observed values to the model predicted values to make sure those look reasonable, and evaluated our residuals to make sure there weren't any strong patterns or trends over time. Now we'll get into the model results for our base run and some of our sensitivity analyses. First, I just want to show you a summary of our data. This is produced by the software, and along the x-axis is the time series, and along the y-axis are the data sources. And apologize because of the scale, you can't see them all, but you can see the little dash indicating that one's there. And then the color indicates that if the color is there, indicates the data were present. And you can see that for 91 through 2017 time series, we have quite a bit of data going into the model as far as, catch, survey indices, length, conditional age at length. That's really just your age data, and then also discards. So our Hessian inverted. Our final convergence level was slightly above the 0.001, but this is normal for models with like a lot of parameters like we have here. We have tens of parameters, over 100. And so as long as it's less than 1 is sort of the rule of thumb I've come across, then you're still okay as long as everything else looks okay. We had some, out of 111 parameters that were being estimated, 4 were hitting their bounds, but this didn't cause great concern for the reviewers, and so we left it at that. And then our jitter analysis, that's that analysis where you're varying the initial values that supported that we found the global solution. So what you're about to see are the results of our final base run that was presented to our managers. So you can see predicted recruitment, and our y-axis is in thousands of fish. Just like our abundance index for age 0 recruits, it's variable over time series and declining, especially in the most recent years. It's dipping down into concerning levels. And we'll talk more about that towards the end of the presentation. Our female spawning stock biomass, this is the mature portion of the stock, is shown here. It peaks in the late 1990s, the early 2000s, and then generally declines through the end of the time series. And this is in units of metric tons. Here we have predicted numbers at age shown in what is known as a bubble plot. And each bubble represents the relative size of a cohort in that year and at that age. And you can see, I'm not sure if you can see my mouse, but if you follow diagonally, like starting at say 1995 at age 0, and then 1996 at age 1, you can follow that cohort through time. And you can see generally as you move from left to right, as you're getting in more recent years, that we're getting fewer and fewer large year classes appearing in the stock. Here we have predicted biomass at age, and we can see most of the weight of the stock is coming from 2 to 5-year-olds. Again, this is just like the previous one, only the size of the circles is proportional to the weight instead of numbers. But you can again follow diagonally the cohorts through time. And as in the previous graphs, you can see that there's fewer and fewer. The overall size is declining as we get into more recent years. Predicted fishing mortality is interesting. It's relatively stable from the start of the time series to about 2011. Then it has this spike in 2012, which I'm not sure we completely solved what the reason was for that spike, but it occurred in almost all of the different runs we looked at. It has a tying of there being high catches and not a lot of, lower numbers of fish was part of that. And so now we'll talk about stock status. So here in North Carolina, we try to define two types of reference points, one in terms of stock size and one in terms of, two in terms of stock size and two in terms of fishing mortality. And we use both targets and thresholds. So for stock size, we define our reference points in terms of female spawning stock biomass, or SSB, and that would be measured in metric tons. And our target is SSB at 45% SPR, that's spawner potential ratio, and that's just the spawning potential relative to a virgin stock. And then our threshold is SSB at 35%. Our fishing mortality is a numbers weighted based on ages 3 to 5. That's the definition of our F that we're using in the assessment model. And our target and threshold are complementary to the stock size. So a target at F 45% and a threshold at F 35%. How we determine stock status is relative to the threshold for stock size and fishing mortality. So for stock size, if the current stock size is less than our threshold, which is SSB 35%, that's female SSB, then the stock is overfished. For fishing mortality, if the current F is greater than the threshold, or F of 35%, then overfishing is occurring. And current is the estimate in the terminal year or the final year of the stock assessment. And in this case, that's 2017. Here we have our estimates of spawning stock biomass over time, and the gray line with the black dots. And the solid line represents our threshold, or SSB 35%, and the dash line represents our target, or SSB of 30 or 45%. And you can see that since 2007, SSB has been below the threshold and the target, including in our terminal year of 2017. So SSB in 2017 was only 35.6 metric tons, while our threshold of SSB 35% was 121 metric tons. Our target SSB 45% was 159 metric tons. Because SSB in our terminal year of 2017 is less than our threshold of SSB 35%, the stock is considered overfished as of 2017. This graph shows our estimates of fishing mortality in the gray line with the black X's. The solid black line is our fishing mortality threshold, or F 35%, and the dashed line is our target of F 45%. And you can see that for, since about 2004, we've been above the target and the threshold. 2008 could be right there on the line. It's hard to tell with this plot. But most importantly is that in 2017, we're above both the target and the threshold. So our current stock status relative to fishing mortality described here. Our terminal year F in 2017 was 0.27, while our threshold of F 35% is 0.18. Our target F 45% is 0.13. Because F in our terminal year of 2017 is greater than our threshold of F 35%, overfishing is occurring. So our current stock status as of 2017 is that the stock is overfished and overfishing is occurring. I'd like to tell you a little bit about our peer review process, and that's tied to whether or not the stock assessment is suitable for management. So all North Carolina stock assessments are subject to external peer review, and this provides an independent peer review. And of course, our goals are to ensure the results are based on the best science available and provide a valid basis for management. And our review workshops are open to the public. Starting in before 2017, we had more desk reviews where we would email our stock assessments to selected peer reviewers, and ask them some questions and they would respond them. But starting in December of 2017, we began doing in-person peer review workshops that's more similar to what the ASMFC and the federal labs do. So there's better interaction, and I think it gives us and we end up with a much better stock assessment. So we ended up having 2 peer review workshops for striped bass. Our initial workshop was in person in December of 2019, and their concerns were the external fit to the Von Burt age length model. There were some issues there. I don't think I showed those. I showed you our better fits. There were some residual patterns in the fits to the length comp data, which could have been a result of model misspecification, and the failure of the model to capture observed trends just in general. So they concluded that the model results were not suitable for management use and agreed to perform a second review after addressing those concerns. Well, what happened is in addressing those concerns, we found a major data error that just totally invalidated the first model. And we identified and addressed that while preparing for the second review workshops. And we addressed that, which took care of most of the other issues. And so the results were endorsed for management for use for at least the next 5 years. Our stock assessments are updated every 5 years. So that's why we ask if will this be good for the next 5 years? They concluded that the stock status determination was consistent with professional opinion and observations. As far as recommendations, they recommended that future assessments consider key abiotic and biotic drivers of poor recruitment, and abiotic factors such as river flow and key biotic factors such as catfish predation and competition. And that sex-specific growth data be collected to better inform growth estimates and length or age-specific natural mortality estimates, and also to resolve the concern on growth estimates showing little difference between the males and females. If you recall the Von Burt parameters, they really weren't different between the males and females, and this was one area of concern for the assessment. So our assessment, the terminal year was 2017. By the time we did this review, we had the data through the second review, we had the data through 2019, and we were interested in showing the peer reviewers what was happening with recruitment. So here we have the relative abundance from that juvenile program 100 survey. And we have a nominal index, that's just the mean catch per toe, and also a GLM index. And you can see that in the final 3 years of this time series, that recruitment is near zero. And I can tell you that through 2021, this trend is still continued despite optimal flow conditions, especially this year. So while the peer reviewers, did approve the model for management use and were confident in the declining trend in recruitment, based on assessment results from the Program 100 survey, there was a lot of uncertainty in the potential causes for the decline of the recruitment. One of the key uncertainties was related to the impacts of changes in river flow on young a year or age zero abundance. And so the reviewers felt predation by blue catfishes could potentially impact recruitment of striped bass directly, or could influence food resources for striped bass through competition for prey. The reviewers also suggested future assessments consider formally incorporating the flow recruitment relationship into the model, as spring flow conditions are believed to influence recruitment and ultimately stock abundance. And again, also consider the factors such as blue catfish that may be influencing abundance, things that aren't tied to harvest. And with that, I thank you for your attention, and I think Gary wants me to ask if you have questions.